Good afternoon, sir. So this will be a progress report on my thesis. So I've started working on the CAD model for the quadrupedal wheeled robot. So my like you said, the master's thesis topic will be the CAD model for a quadrupedal wheeled vision guided robot. So I started making some inquiries. I started doing some research to begin with to get the dimensions, physical size of the robots. So for the physical size, I found that for that since it will be used for mostly delivery services, yeah, it has to physical dimensions doesn't have to exceed that of the walkways and the footways on the road. It's going to have to share those parts with normal passers, street users. So I obtained some information about the dimension of street usage and found that the at least the maximum permissible width for the robots will be around 1000 1.5 meters. It will be around one between 1 meter to 1.5 meters. So I chose a length of I ended up with a width of 1.385 meters. That's approximately 1400. Sorry, a width of 1385 millimeters. That's approximately 1.4 meters. And then for the heights of the pavements on the road were around 70 millimeters. Most of them they were 70 millimeters high. These were already designed for people who use both wheelchairs and motorized wheelchairs. So they were considered when designing the road. And luckily for this design process, it serves an advantage. It serves as an advantage since the total width, since the total height of the robot doesn't have to be that high again, and the most roads in the UK are already level, so it will be easy for a robot to maneuver. So I chose a length of 400 millimeters. That's approximately 0.4 meters, I think. Then after doing that, the for the mechanical design, the most important part will be the limbs of the robot. That's the first link here, and this second one here. So designing them with the right actuators and the right number of degree of freedoms. So I proceeded to design the components that will be needed. I started designing the various components that will be needed and the motion and power transmission systems. So this is the level where I'm at the design now. Let me try to explain this. Isolate. So this is the link of the robot. This will be in the upper arm, the forearm of the robot. So this link is approximately 400 millimeters in length, as shown from this rough sketch, and there will be two of them. There will be two of these links available. They will be responsible for carrying most of other loads. Okay, isolate. Yeah, there are two of them, this one and this other one. So I after considering the weights of the bots of the robots and the load that is going to be carrying, I found this actuator to be right both geometrically and strength wise. He has it to have the payload to leave the robot. Isolate. So this is a clear path servo. I'll be including the power rating, the payload, basically the data of the servo in my reports, in the report I'll be sending. But I found it that this servo will be ideal for the limbs of the robots. So as there are two of them in the link, there are two of them in this one link, and this one here is responsible for moving these joints at this end, while this one is responsible for moving these joints and the joint at the other end. For transmitting, I thought of a way of transmitting the power from the servos to these joints to actually move them. So I came up with this gear assembly design. So this gear comprise of a bevel gear, and this bevel gear is linked to another bevel gear, which will be used to transmit power and motion at 90 degrees from between two axes that are perpendicular to each other. So and this bevel gear here, the one on this shaft, is mounted on a normal spur gear, and this spur gear is linked to this another spur gear at this end. Same thing with this other side, in order to enable motion and power transfer. And this set of gears here, they are mounted on a shaft. The diameter of this shaft is diameter of 10 millimeters, that's around 10 cm. So I'll be making a design. So I'll be designing these shafts. I will analyze the stress using NS and SolidWorks, and also this Fission 360, which is the one I'm using now. I'll be running the analysis. Then I'll also make like a manual design like you taught us in our first semester machine design to show the stresses on the shaft. So I'm planning, there are bearings at this joint. There are two bearings at this joint, and this joint design is made in such a way. Let me make this. So this joint design, the green bearings here, they are cross roller bearings. They are capable of bearing both axial and radial stress. So I found that they'll be perfect for this application, since the robot will be under various stresses. So I have another of those bearing at this other point. So if I should make this bearing, if I should erase the visibility, yeah, so inside this bearing, this link here which is part of the third link. The first two link I showed at the first were the second link. These ones are part of the third link. They are connected to this knot, and then this knot is directly bolted into them, but they will be able to rotate about the axis because they are both connected to, let me make the bearings visible. because they are both connected to this bearing, which is connected to the first link. So they'll be able to rotate freely about the axis. So I've used the gear design tool in this software in Fusion 360. So tools, add-ins. So there's a tool here for designing spur gears where you put in all the dimensions and properties. So I've used that tool for the design of the gears. And if I should go to inspect and check for interference between these two spur gears that mesh, that transmit motion between each other, so there is no interference. And between the three of them, there is no interference. And if I check add this other two that mesh as well, there is no interference. So I went ahead to use the motion linking property of this software to link the motion between the two gears. So I'll make everything visible to this demonstrate. So if this link here should move, the motion will be transmitted to this other link. If this servo should move, therefore moving that spur gear, the spur gear transmits the motion to this link by the aid of the gears that are meshing with each other. So if I animate the model, we'll see how this happens in real time. Reverse position, animate model. So basically what's happening is that this spur gear is rotating, transmitting the motion to this one, while this one transmits it to this other two, to these bigger gears here. I have a velocity ratio of about 2.5. So I wanted it to be lower so that there will be more torque at these joints here. Though I'll try to see there's a way of adjusting the velocity ratio so it's going to match, also that a nice velocity and torque can be obtained at these joints here. So that's basically what I've done so far. After creating the CAD model, I'll start writing the reports. I'm currently gathering the materials for the reports, and I've written the abstract, but I found that without the CAD model, and there might not be really much to discuss in the report. So that's how far I've gone. I thought I should make this video. Then I also submit a typed version of this report to you. Thank you very much.